Hello everyone, it's me, Mr. Younger again. I'm here to work yet another linear expansion problem. I want to warn you initially, those of you who are in my class, there is a problem very much like this one, but innately different, so don't confuse it for the other one. This one is just asking, hey, if I got a brass plug and a iron ring, how much heat or how much temperature change has to occur on the iron ring so that the brass plug will fit into it. Whereas the one on the homework and therefore in the mastering system, they're actually asking what common temperature the two things, the brass plug and the iron ring, what common temperature they have to be brought to so that the plug fits inside of the ring. In this one, I'm using the idea that it takes a little bit of tolerance. In other words, you can't just make the outer diameter of the brass plug match the inner diameter of the ring and assume they're going to fit. You actually have to have a little bit more play in that. So I'm taking that into account. And it might actually give me very unrealistic numbers because I was trying to give you guys a hint on how to go about doing the homework problem, but without giving you too much of the information. So let me go ahead and share my iPad screen with you guys. And here we go. So that should be coming up any second now. So again, I will be using the table in the author's book, in Gene Coley's book. And in his book, he suggests that the coefficient of linear expansion for iron or steel is 12 times 10 to the negative 6, which remember, that's also roughly what it is for concrete, according to him. And that's an important thing, again, from an engineering and building standpoint, specifically with reinforced concrete. So let's go ahead and solve this problem. The problem says a brass plug is to be placed in a ring made of iron. At 18.0 degrees Celsius, the diameter of the plug is 8.758 centimeters, and that of the inside of the ring is 8.743 centimeters. If the plug must be 0.002 centimeters smaller than the ring's inside diameter to fit, at what temperature must the ring be heated to? I should say to what temperature the temperature must be, or the ring must be heated, and then I wouldn't end in a preposition, but it's my understanding that that's an old rule, no longer valid for English, so I'm not going to worry too much about it. So here's our solution. Again, what I'm going to make use of is the fact that alpha for steel or alpha for iron is 12 times 10 to the negative 6 Celsius degrees to the negative 1 power. And I'm going to say the initial temperature of the ring, which I'll just say Fe because it's iron. The initial temperature is 18.0 degrees Celsius. I'll also say the initial length of the ring, and I'm specifically talking about the inner diameter of the ring, even though I'm using the same symbols that we use in our equation, which I'll give you again in a second. But the original diameter of the ring is 8.743 centimeters. And of course, the original diameter of the brass plug, which I'll just indicate with a B for brass, that initially and finally, because we're not changing its temperature at all, is going to be 8.758 centimeters. What I need to do, though, is I need to make the final length of the iron. I need to make that 0.002 centimeters larger than the actual brass plug, and that is 8.758 plus 0.002 centimeters, which is obviously 8.760 centimeters. Now, the equation I'm going to use is either delta L is equal to alpha L0 delta T, or the one that I like better and the one that I'm going to use this time is the final length is equal to the initial length times 1 plus alpha delta T. So that's what I'm going to use. Don't know why I keep writing that as a parenthesis instead of a square bracket, but here it is. So that's the equation I'm going to use. So let us begin. I want the final length of the iron to be 8.760. Again, remember, this is the inside diameter of the iron. A big principle behind this that you might not get yet, especially if you didn't read the book, is that if, for instance, you heat up, let's say this is a plate of aluminum or something like that instead of the cardboard box that it is. And it would actually work with cardboard as well, just maybe not quite the cool effect. But either way, if you imagine this was just a sheet of aluminum in the shape of a rectangle, when you heat it up from some temperature to a higher temperature, it's going to expand in this dimension, left and right, but it's also going to expand in the up and down dimension as well. But the big question is, because your book explicitly says, hey, every dimension of the object will expand according to this equation. So what if, for instance, this big metal plate had instead a hole in it? What would the hole do? So to think this out, in case it wasn't obvious to you, the hole could be affected such that this dimension got bigger and this dimension on the other side of the hole got bigger, and then the diameter of the hole would get smaller. But what we see is that would actually introduce a really weird problem in that just heating up a metal causes it to tend to bend or put stressors on it that it wasn't meant to have, and that just doesn't seem very physical. So in fact, what we know happens is a hole in the aluminum plate is going to act just like the piece of circular aluminum that we took out of the plate. So I'm treating this inner diameter, which is really just a hole of air, I'm treating it just like the diameter of a disc of iron. So that's how we're working this out. So in this case, the quote unquote disc of iron that would fill in the ring should have this new length. So I'm going to say 8.760 centimeters is equal to the old length, which is 8.743 centimeters, times 1 plus alpha. In this case, we know alpha is the same as it is for concrete, which is 12 times 10 to the negative 6 reciprocal Celsius degrees. So that's Celsius degrees to the negative 1 power. And then I'm going to multiply that by the change in temperature. What I really want to know, of course, is the final temperature is the question mark. So I'm going to put T minus 18.0 degrees Celsius. That's what we're going to solve. So we solved this for T, and that should give us our final temperature. Again, I took these numbers more or less to be like the ones in the problem, just because I was trying to give you a little bit of hint about the problem from the mastering website. In the mastering website, they're doing a much more complicated problem, but I think you can see from there how to get it started. The main thing here is we're going to be solving for the temperature T, and I'm going to choose to divide both sides by 8.743 centimeters first. That's not the typical way that it's necessarily done, but I kind of like it, so I'm doing it. 8.743 centimeters, 8.743 centimeters. Now, when I do 8.760 divided by 8.743, I get 1.001, and then the digits are 944. Now, we actually have a subtraction going, I mean, a division going on here, and it's a division between 4 sig figs and 4 sig figs. So that means we only have 4 sig figs, which means the 9, the 4, and the 4 is, in fact, non-significant digits. So those digits are not significant, but we're going to keep them for all the intermediate calculations. And then on the other side, I'm going to go ahead and carry out this multiplication. For starters, I'm going to take the 12 times 10 to the negative 6, and even though it's not first, I'm going to go ahead and multiply it by the negative 18. So 12 times 10 to the negative 6 times 18.0, that leaves me 2 sig figs, and it's a minus, so I'm going to put a minus here, and the answer is 0.000217 6. Now, in this case, we multiplied 12 times 10 to the negative 6 times 18.0, so we had 3 sig figs. That means that the 216 is in fact all 3 sig figs, but the 0, oh, no, we did multiply by 2, so the 6 and the 0 are not sig figs. Okay. Now we're also going to take the 12 times 10 to the negative 6 and multiply that by the t, and of course that's going to give us a positive 12 times 10 to the negative 6 reciprocal Celsius degrees times T. Now, to solve this equation, I can go ahead and do 1 minus 0.0002160. 1 minus 0.000216 gives me 0.99974. Now, remember that 1 was to an infinite number of decimal places, so I could have written 1.000000000, any number of decimal places I wanted. And when I actually did the subtraction, what dictates what the sig fig is the number with the fewest decimal places, which in this case was the 0.0002160, and the 1 is the place where it was at, which is in fact the 5th decimal place. So what that's going to tell me is that the 8 and the 4 are not significant figures, and we still have the 12 times 10 to the negative 6 Celsius degrees to the negative 1 power times t, and we still have the 1.001944, where those three are not sig figs. So what I'm going to do now is I'm going to subtract 0.9999784 from both sides. 0.9999784, which the 8 and the 4 are not sig figs. So when I do that, I do 1.001944 minus minus 0.999784, and that gives me 0.000, there's my pot of 3, 410, and then there's another 4 over here, of course. So this tells me from my basic math, of course, that really only the first 3 are significant digits. So the 4104 is not significant. And in fact, that would come up to be 0, which is not very reasonable. But either way, we're going to work with it because that happens when we're doing linear expansion. Unless we're dealing with stuff really, really big, there's a high probability that the size change might not even register in the sig figs. So in this case, what I now have on the left-hand side is 0.0004104. Yes, I guess that works out right because I could divert. Yeah, okay. And of course, the 4, the 1, the 0, and the 4 are not significant. And on the other side, I have 12 times 10 to the negative 6 reciprocal Celsius degrees times T. So now what I want to do is divide both sides by 12 times 10 to the negative 6 reciprocal Celsius degrees. Of course, like I said, whatever you do on one side, you must do to the other. So times 10 to the negative 6 reciprocal Celsius degrees, which is going to make that Celsius degrees, which we can change to degrees Celsius. So 0.00414 divided by 12 times 10 to the negative 6 gives me 34.200 is equal to T. And actually, I should go ahead and include that unit there. So let me do that first. I put a bunch of extra sig figs on there so I could mark out exactly what it is, but this is going to be degrees Celsius is equal to T. Now, what we do have is essentially no sig figs divided by two sig figs, so it's not reasonable for us to have any more than actually, since we should not be able to calculate it at all. So all of these digits are technically not significant, but what I'd have to do is maybe do something like that. But the main thing is we suspect the temperature must be at least 34.2 degrees Celsius. And that should be it. Of course, you can go back and put that into the equation for L equals L0 times parentheses 1 plus alpha t to make sure that it in fact lengthens it by the amount necessary. And if you found that to be the case, you'd be more confident that you didn't make any careless mistakes. But that is how the physics is done for this particular problem. I hope that helps. And that's about it. Let's have a good day, everyone. Bye-bye.